Let's start. Our first presenter for today is Prashant, and he's going to talk to us about how we productionized Hudi's metadata table at Uber, how we can perform A/B style testing with data pipelines, and much more. Over to you, Prashant.
Thanks, Nishit. Hello, everyone. I'm Prashant, and I'll be talking about optimizing Uber's SDFS file listing using the recently released Hudi metadata tables. So I've been working at Uber for last 2.5 years. I'm a senior software engineer here, and I've helped in the design and implementation of the Hudi metadata table. Currently, I'm working on the Hudi native indexes, which is the record level indexes. And I also delve into testing and data validation at scale. So that is among all my interests right now. In this presentation, I'll talk about the scale at Uber, which is the primary reason why we had to solve it through the metadata table. I'll talk about the solution. I'll also talk about some of the background work we had to do, especially because we were rolling out at large scale in production. And finally, I'll cover some challenges which we faced and some of the work we are continuing along this direction. So at Uber, we have a very, very large scale for Hudi, probably among the largest in the world. So we have around 8,000 tables in production right now. These are the supported tables. A lot of other teams work with more number of tables which are experimental in nature. And around these 8,000 tables, we have 5 million commits per day. This is the Hudi data commits. And we are performing around 200,000 plus cleans per day on all these data sets. And because all the Hudi operations require a lot of list status on SDFS, we are already reaching a peak of around 40 million SDFS list status calls per day. And this last stat is the one which is the main problem which we were trying to solve through the metadata table. So as you all might already know, Hudi operations require many SDFS list status calls to figure out the partitions on the disk, the Hudi metadata, the Hudi folder listing, the timeline, and all of these in the SDFS world end up being a list status call on the name node. Now, with large number of tables, the number of list status call just grows very, very high. And this leads to a problem because the SDFS infrastructure sometimes has latency spikes because of these large number of list status calls, or when we do backfills, we onboard newer data sets. This causes additional overhead. When we are rolling out more and more Hudi features, like we rolled out clustering, we are doing async compaction, all of these features again require more list status calls. So to scale Hudi at Uber, we have to look into reducing the total number of list status calls. Finally, the cloud stores also throttle the list status calls. So even experimenting with cloud stores requires reducing these list status calls. So because all of these problems highlighted at a particular Hudi problem of listing a lot, we designed and implemented Hudi metadata table last year, which is the solution which helps us solve all these problems. So in very brief, you can go and read the metadata table RFC, but in very brief, metadata table saves, it's a key value cache, which saves the partitions and the list of files within the partition inside it. It's a Hudi MOR table within the data set itself. And instead of now doing list status calls onto SDFS, the code can just go and read this key value pair from the metadata table itself. And that is a very, very quick operation taking milliseconds. And this reduces all the load on the SDFS infrastructure. Now on our end, we have rolled it out to all the tables in production. So that's those 8,000 tables. And some of the highlights of a rollout were we required no downtime, and we did not have to stop any pipelines for the rollout. We reduced it to a single config change across the clusters or pipelines to disable this feature at runtime. We had inline bootstrap of all the metadata tables. We never had to stop or we had to miss out on our SLAs. and I've highlighted for our largest table, which has 1500 plus partitions and 12 million total files. The total bootstrap time was less than 10 minutes. So we really optimized the bootstrap of these tables, which also helped us in disabling the table, re-enabling the table at will without having to worry about missing SLAs or slowing down the pipelines. And we did an incremental rollout to the tables based on size and the priority, starting from the lowest priority ones and the smaller tables going up to the largest one. We have 100% monitoring and validation of the tables, which means that every single day, each of these metadata tables are validated against actual data on the SDFS. And this we have been doing from day one of the rollout. And currently we are running metadata table version 1 in the 08 plus, and we are testing metadata table V2, the new design, which is implemented in Hudi 010 plus for rollout. Now, this slide shows you the immediate impact we had the moment we rolled this out. So these are two different graphs from two different clusters I've highlighted, where you can see this is capturing the total number of list status RPC calls we were generating from these clusters to the name node. And we immediately see that as the rollout happened over a period of entire day to the various pipelines, the list status call immediately dropped nearly to zero. It's very close to zero. And this is only tracking the list status calls in the outside the .hudi folder. So .hudi folder is not covered through metadata table as yet. So this shows you the impact, immediate impact of enabling the table. We have already removed 17 million plus list status calls from our data centers. And we are on track to remove a large number of other ones as we roll out to other tools and features. We face zero production issues or SLM miss or any data quality issues during this rollout. So I want to highlight our vision towards this project because we had such a large rollout. So we wanted to reduce any kind of issues on rollout. So we worked with the vision of identifying the issue, collecting all the data beforehand and tracking it as we went along. So we did some background work. One of them was, in the interest of time, I'll just talk about things which are specific to us, which we did. One is a metrics registry where we collected a large number of metrics from all of these executors. We developed a replay testing tool, which allows us to use the production data sets in a read-only manner to test workloads and performance features. And we have a validation tool which validates the metadata table every single day. So I'll just quickly go through some screenshots of the thing. So this metric registry allows us to collect very fine-grained metrics. Like here I'm seeing we can collect all kind of RPC calls to the name nodes. We can collect the timings for various operations. We can even collect the rollout stats and the various versions in production, bytes written, and all these kind of things. The validation tool similarly collects, it works on all the production data sets and can figure out which data sets are valid, invalid, and it runs very quickly to validate the data sets. Now, this is one of the tools we developed, which allows us to test production data sets. So we use the production data sets in a read-only fashion, and we implemented an overlay file system in Hudi, and all the writes then get diverted to a temporary location. So we can use an existing large data sets, which are at very, very high petabyte scale to do all our testing of this metadata development and for performance figuring out. So it allows us to do very fast, realistic testing. And this slide shows in more detail how this tool works, but in the interest of time, I'll skip that. I mean, we can cover it in the chat if required. So one of the things which I wanted to highlight through this entire process was what kind of challenges do we face at this scale? So this is important because we are going to release more and more similar features at scale, and this helps us envision those problems in advance. So one of the things which we faced was how to test at such a large number of with large data sets with millions of partitions and files. So unit tests and integration tests don't work when you want to test bootstrap with a million files or you want to test with 1500 partitions, right? Generating them in unit test and integration test is really hard, time consuming. So we created this replay tool, which can help run these experiments on existing data sets without affecting these data sets. So that really helped us. And we also found that error conditions are not covered through the unit tests in Hudi, like all the SDFS issues, like server busies, network issues. Sometimes the files don't close. Sometimes the files don't get created, renames fail, things like that are not covered. And we found many of these issues in production. We could quickly identify and fix this also because of the validation tool we have. And because the bootstrap process is really, really optimized, we could quickly recover from such issues. And when we finally release such features on very large number of tables, having metrics and alerts already in place, having something like a rollback plan and having a validation tool in plan really helps you recover from any issues which might come up, because monitoring manually such large number of data sets or even through graphs is very difficult. Finally, I wanted to highlight that metadata table issues appear in two types of issues. Like you could have extra files in the metadata table, or you could have missing files from the metadata table. And right now, the only way we have to fix it is through code inspection and through SDFS audit logs, where we can go through the trail of which files were created through which experiment. It's not a very easy process, but having all this data just helps us go through it. We did not find many issues. They were rare, but when we found them, it was easy to debug them using these processes. And finally, we are continuing the work along this line of releasing more features in the metadata table. Like we are currently working on Hudi native DFS index, which is under testing. We are rolling out these to all our query engines. We are also rolling out metadata table v2, and we are also helping design the Hudi column level indexes, which can index any column in Hudi as like a secondary index. So these are some of the very interesting large scale future work which we are continuing in 2022 on top of this release. So as Nishit already said, we are hiring, and if you would love to solve all of these and more problems at Uber scale, we'll be happy to have you on board. So please do apply at this email address. And finally, thank you everyone, including all the developers and the community, which helped us through the design and development of this. And we are very grateful to all of you. So if you have any questions, I'll be happy to take it on the chat in the interest of time. So thank you, everyone.
Thank you, Prashant. It's especially cool to see you share some learnings on how to perform these data validations at scale. I think with like extremely large data, it gets really tricky to keep SLAs intact while releasing large features. So thank you for sharing that. And yeah, folks, if you have questions around that and you would want to know more, please please leave questions on the chat box, and we can connect more. All right. So next up, we have Felix, who is going to talk about use cases at Philips and how they use Hudi to solve some of their critical data needs. Over to you, Felix.
Hey, thank you. Yeah, I was in mute. So do we have the slides, or I have to present?
Yeah, I think you can share slides, Felix, your own slides.
Oh, okay. So yeah, okay. So give me a second. I'm sorry. I'm just trying to. So I'm having trouble on presenting. Give me a second. Don't see a provision to share. Give me a second. Okay, yeah. So now I can. Yes. Hi everyone. So today I'm talking about how the data lake house powered by Hudi is helping us in Philips to solve some of the problems that we have. So who am I? So I'm a system architect at Philips. And I have 15 years of experience in different domains, especially on the telecom, banking, and healthcare. I'm currently working on designing and implementing the transactional data store or a lake house and its data architecture, especially the cataloging, canonicalization, modeling, and etc. Also involved in the event streaming and event stream processing at scale. So especially my passion is evaluating and learning new technologies and architectural patterns and leveraging them in the design and implementation. That is how I can come across finding out solutions for our problems, come across Apache Hudi. So why we need a transactional lakehouse? So at Philips or and any such big companies, so we will have different business units and different applications, large scale applications. And we have data silos. So the applications will be storing in its own transactional stores, its own choices like SQL, Postgres, MySQL, or MongoDB, those kind of things. And also in different formats, like it's either it will be pre-aggregated, non-aggregated, or it is not standardized across. So you have a lot of silos, and these applications, you won't be able to achieve the data-driven information that we are looking for. For example, the data silos, so the analyst cannot run queries because the data is not available. Yeah, the entire full picture of the data won't be available. And differing quality, that is the biggest concern of any data silos. That's part of data silos. So everybody has their own data in their own qualities. So it won't be easily merged, and like you should not be able to derive insights from those data. Then not having a centralized data analytical store or a lakehouse, it's impossible to do the analytics on a transactional store. So it's not meant for it, it's not efficient. So you won't be able to do the analytics and the data-driven insights or any machine learning, things like that. So then having no standard format, because every application has their own needs and their own requirements. So they might have the data in different formats. So for having no common vocabulary, it's not able to run ad hoc queries or any of these analytics, since some data is aggregated, some data is non-aggregated. So the other thing is the data processing itself. So there is no centralized data processing. So the data, like every application has their own data processing, things like that. So there is no data processing. That data processing is duplicated. So it's that was another problem. So, and this is data view of our house with respect to the 5 Vs. From a volume perspective, we are talking about terabytes of data created every year. So we have millions of IoT devices sending data to our system. So then we have to support structured, semi-structured, and unstructured data from a variety perspective. And from velocity perspective, we are getting billions of data records or events every day. And we need the requirement of streaming and batching batch needs. So it needs to support both the work heavy, like write heavy, as well as the read heavy workloads. From a veracity perspective, so we have to ensure the data quality, the data we have to have the catalogs. The every big data engines can just run on a unified API. So then the data governance and the canonicalized, the data should be canonicalized. So then from a value perspective, so it needs to the lakehouse will be the source of truth for the business intelligence and visualization, machine learning, these diverse workloads like the data exports, data analytics, and explorative analysis, etc. So these are some of the from a consumption perspective, what value it is bringing in. So this is the architecture that we are currently using. As I showed, we have different applications. So those applications will be doing the canonicalization of the data and streaming it over to Kafka, and then using Spark structured streaming jobs plus Hudi, we are ingesting the data into the Hudi S3 lake house. So once, like, we have a layered architecture in the lake house. So we have silver layer, golden layer, etc. as a normal lake house architecture. So where once the data lands and using the that is where the Hudi what brings. I will cover that in the next slide, but I will just give a quick intro on that what Hudi brings us. Hudi enables us to do the incremental data pipelines and the processing. So using Apache Airflow, we will just do the pre-aggregation or like the aggregation or enrichment of the data on the silver layer to the specific application layer, that is the golden layer tables. So that way our underlying or downstream access cases should be satisfied in an efficient and timely fashion. So the EMR notebooks or the reporting BI, we are using some like the BI tools or SageMaker. All these things can interact. It's either interacting through the EMR. We are heavily using EMR and the EMR Presto or EMR Spark SQL. So that comes through our centralized access control called like the AWS Lake Formation is what we use to provide or to avoid the data duplication. For example, previously we were doing something like we have to have the data, identifiable data, and then we will have to remove data, the personal information, and have the data duplicated in a different table, etc. With the introduction of the lake formation, now we are not doing any data duplication. That enables us to just hide the data what you want. So that is what we are, our current architecture. And the Hudi brings like, so the fast ingestion, the ACID capability. So those things, it just enables a trustable lake house where the downstream consumers can access the data with 100% guarantee or the trust on the data, because they are not going to see this partial data or anything like that. So that was a big plus or an addition that we were able to get out of Hudi. So this is what the Hudi brings to our lake house. From a data storage perspective, it stores data in the open format. That was the big thing that we were looking for, because no vendor locking. And then it supports hybrid cloud object stores. And another thing was that the AWS EMR was having this Hudi as a primary component. That was another big plus. So also it supports the data cataloging, auto cataloging. Like you should be able to get that one out of the box. It can just sync to the MySQL or Glue data catalog, and that can be used downstream by downstream consumers. From a data ingestion perspective, compared to this, it's the other competing same technologies like Iceberg or the Delta Lake. So the one thing that I just noticed, like when we started the decision time, it supports both the near real-time ingestion as well as the batch, like for the write heavy or the read heavy, that MOR or COW tables was a big part for choosing this Hudi to our solution. Supports the efficient incremental data pipeline jobs via record level upserts and deletes. It was important for us to support the deletes for the compliance, etc., and also upserts. Since IoT devices, we will get because of the streaming and other things, or reprocessing, we may get duplicates. So it was able to help on that front. So then the ACID transaction compliance, and then the multi-writers. So for another thing was like the introduction of the OCC, and then from the disaster recovery via the save points was also an important thing for a production system. So from a data management perspective, as I mentioned already, that the data cataloging and providing a uniform API for all the big data engines, so that auto cataloging, so without much extra work, so we could just using the Spark structured streaming jobs and Hudi and having that Hive sync, it was very easy thing to do. So we were, the other thing was the schema evolution. So we are using Kafka and Kafka with the schema registry, where we are enforcing the schema and evolution. So the Hudi also supports the same. So we were able to just have our entire system or the platform having that schema enforcement and evolution, and not ensuring that nobody is putting anything that is garbage data. So that was an important thing that it helps us to achieve end-to-end. The data compaction, deduplication, and partitioning, so for some of the capabilities, and then the concurrency control. And now we are looking at the data clustering and the auto, and like the data clustering capability. So we don't have that one today in our system. So we are trying to get that data clustering working and to get a little more performance. From a data consumption perspective, it was having, the Hudi is having a great integration with all these big data engines. For example, for us, Presto was one of the main, and Spark SQL, and also Redshift and Redshift Spectrum. So we have Redshift Spectrum support. So those are the main reasons of considering Hudi into our solution. So with those things, so we were able to just to support our interactive analytics as well as the business intelligence solutions with this transactional lakehouse powered by Hudi. So these are some small metrics that we have also from our environment. From an ingestion perspective, you can so as the source is Kafka, the processing it's done by Spark structured streaming and Hudi on AWS EMR. The table type is MOR. The metadata is on the external Hive metastore AWS RDS. And optimization, we are doing partitioning and compaction. So we are getting billions of records every day, as I mentioned. So we are doing the partitioning and then compaction. So then sync is AWS S3. We are able to ingest 200K messages per minute, and each message is 10 records. So we are able to ingest 2 million records every minute into our MOR table. So from a consumption perspective, from an interactive query perspective, we are using Presto DB on AWS EMR. So the source, again, it's a S3 and the MOR table. Some of the metrics that I can see, it's like a 3 to 4 second latency on demand aggregation queries. The benchmarking is done on 1 trillion records. And every day we are having 518 million records. This is a small data set I'm talking about, not the biggest one. So we were doing some benchmarking to see the performance and the evaluation. So why Hudi? So especially the reason why we have chosen Hudi, at the time I was doing the comparison. So I compared Iceberg, Delta Lake, open source, and Hudi. So the main advantages Hudi was having among the other two was it was supporting this multiple table types. So for write intensive or read intensive. So it's like we have that MOR and COW work, the table support. And the Delta Lake open source was missing some critical features from its paid version, and was one of the main reason for like not choosing the Delta Lake at that time. Then the Hudi was available on EMR as a primary component, was another driving, since we were using AWS and AWS services very heavily. So the AWS EMR was having that Hudi. So that was another driving force why we chose Hudi. And we are very happy about the way that we are able to get things working. Then the direct integration with the Presto, Athena, Redshift Spectrum without the need for extra work is another important thing. For example, in case of Delta Lake, we have to create or generate the manifest file. Since we are doing the partitioning and dynamic partitioning on the fly when new data is arriving, so in that case, in case of Delta Lake, we had to use this repair table, etc. So those were the additional work that we had to do. But in case of the Hudi, so we were able to get without those extra work. So the data is another important thing, is the data is available to query as soon as it's written. So no extra work. The another important thing when like the Iceberg and doing the comparison between Iceberg and the Hudi, that Hudi was having that a faster ingestion using the MOR tables, where the Iceberg, it was they were just mentioning that the minimum batch size or the batch interval should be 1 minute or more. So that is what it's recommended. So our the needs were not meeting. So because of that, and also it was missing some integrations with AWS services, and so the lacking documentation on integration. So we were not able to get all the informations and how to integrate with AWS services, and what needs to be done. So those were the reasons, and Hudi was winning, and then so we chose Hudi, and so we are. So now we are able to get this the lake house with the Apache Hudi, and getting all the features that we were looking for from the Hudi. Yep, that's all I have for the presentation. So if any questions, I'm happy to answer.
Thanks, Felix. I don't know if there are questions on the Q&A box. Actually, I'm unable to see it. But if there are, please help answer them on the Q&A box.
Yes, so there was a question. I could see that are the BI tools or reporting directly fed by Presto or EMR? Is there a caching layer or data aggregation pipelines between these? Yes. So what we are doing is, so as I mentioned, it is a layered architecture. So we are having the data in the silver layer, and then we are getting the data into the golden layer in the form that the different access cases are expecting for the best performance. And then, as you know, that most of the BI tools, they have their own elastic cubes, etc. So you will be feeding that data into those cubes using this Presto connector or the Spark connector. So once the data is in their cube, at that point of time, it is just the slicing and dicing will be done on that one. And also for some of these tools that, so what we are using, one of the tools that we are using is called Sisense. They provide two different routes. One is like directly reporting or creating the dashboard on top of the source data itself. For example, the Hudi data, like so where you can just use the Spectrum connector or the Presto connector. So you should like you can just get the data rather than copying that amount of data into that size and elastic cube. But for real time or anything like that, so it's advisable to copy that one, or the slicing and dicing you can just do very efficiently on their elastic cube. So, and why Presto and Redshift? Why not one or the other? Okay, good question. Sometimes like what I was just mentioning is there are some data we have in the Redshift as well. So when we have the data in Redshift, so it's always advisable to use the Redshift spectrum to do the federated query or that query across this Redshift and the Lakehouse. And if that is not the case, if you don't have the data in the Redshift, so then the Presto in most of our access cases, we see that Presto SQL is good enough to satisfy the needs of querying the data directly, the Hudi data directly, and to get the best performance that, as I mentioned, so on demand aggregations of 3 to 4 seconds, we're able to achieve. Okay, so
Great.
yeah, so I just, yeah.
Are those all the questions, Felix? Sorry, I'm
Yeah, so there was another question like, so what were the contenders of this Hudi? Like, so as I mentioned, so we were having the three data management tools today. In my understanding, one is the Iceberg, one is Delta Lake and the Hudi. And as I mentioned in this slide, so this was the reason we chose Hudi. These were the reasons that we chose Hudi, and we can see that the fast ingestion and write heavy and read heavy workloads that it's efficiently supported. And then it is like now if you see that Apache Hudi was at that time, it was the Apache Hudi was the only primary component on the AWS EMR. Now they have Iceberg also. But the Iceberg, one thing that was missing is the fast ingestion. So that was one. So overall, all our requirements were met by the Apache Hudi from that Lakehouse architecture perspective. So that was the reason we chose the Hudi.
Thanks. Thanks, Felix. Yeah.
Thank you.
Yeah, if there are more questions, folks, please feel free to type in the Q&A box, and Felix, hopefully you can answer them on text. Yep. But like, thanks for sharing all the details about the architecture. Very cool to see, you know, the latency at which you're able to ingest all of this data and how merge on read tables are being helpful to you. It's very awesome to see that. Next up, we have Bhavani Sudha, who is going to talk to us about Hudi's use case at Moveworks. Bhavani is also a Hudi PMC, and later she is going to share Hudi's OSS roadmap as well, and what you can expect in Hudi's future releases. So please stick around after she discusses the Moveworks use case to understand all the cool upcoming features. Over to you, Sudha.
Thanks, Nishit. Sharing the screen. Is my screen visible?
Yes. Do you want to put it in the presentation mode or? Yeah.
Okay. Welcome, everyone. I'll be presenting how Apache Hudi powers data lake at Moveworks. My name is Bhavani Sudha. I'm a PMC member with Apache Hudi project. I'm a software engineer at Moveworks. I focus on building data lakes and data platform tools for analytics. Who is Moveworks? Moveworks is an AI company that automates support at work by bringing in enterprise conversational AI for enterprises. Moveworks is able to help companies support their employees who have questions on a range of issues like IT issues, HR updates, policy changes, etc. And data analytics is a critical backbone for this mission. And in this talk, I'll be going over how we have been able to successfully use Apache Hudi for our data lake needs. So this is our agenda. I'll go through the previous architecture, what are the requirements and challenges for moving towards a data lake-based solution, and how Apache Hudi fits our work. So this is our previous architecture. So the Moveworks AI platform is powered by many microservices that interact with each other to understand and respond to users engaging with the Moveworks chat application. And these microservices produce logs, which are the source of truth data for our data analytic needs. These logs are shipped to Amazon S3 periodically, and we use Apache Airflow to orchestrate ETL pipelines that are Spark-based and run on top of EMR to consume these logs, process the data, and produce the data to Postgres. Then our querying layer kind of queries Postgres for various analytical needs, like notebooks, superset, and other dashboarding tools. This was fine to start with, but we very soon hit cost and performance issues. And so we had to look out for other options. As you can see, Postgres is used for the storage and the compute model. So we had issues and like we had different considerations when we were trying to move out of this architecture. One is storage cost. Like, you know, RDS instances are charged based on uptime and not based on usage. And like based on the nature of our application, we didn't have to fully utilize these servers at all the time. So there were also idle times where we were still paying full cost for storage. So that was one motivation for us to get off of Postgres into a more loosely coupled architecture, like a data lake based architecture. And while we enjoyed very fast query results from Postgres, we were still paying the storage cost, right? So we were looking to see if we can take some trade-off in the query results, like some reasonably query results, but at the cost of lower storage cost. So that was another consideration. We were also, like with every maintenance activity in Postgres and backfill sort of operations, we had to constantly monitor for production queries not being affected. So this would have been much easier if the storage and the compute had been decoupled, and we can scale them separately. Then we also had flexibility issues where we were looking to explore ad hoc data, like semi-structured and unstructured data. This was tedious in a more strict traditional system like Postgres, where schema is upfront enforced. And so what this was difficult to achieve in terms of changing our ETL pipelines to fill these gaps before syncing to Postgres. So it was time consuming, and we had to look for ways to work around this. And finally, we were also looking to see if we can reduce our query cost by moving to a usage-based pricing model. So with these, we were considering S3 and Athena for towards our data lake solution, where S3 would offer like cheap storage solution, and Athena would price based on usage. However, coming from like relational DB, where there are like rich APIs, moving into a data lake solution was not a easy feat with just S3 and Athena, because these are like independent systems, and we have so many challenges that we need to fix for the gap that the previous system had offered. So some of the challenges that we identified were these. First off, like we wanted queries to give like a consistent view of the data always. So for example, we didn't want the ongoing ingestions to show up on queries. So we needed some sort of an isolation between the readers and writers. And then our logs always had duplicates, either due to retries or like at least one semantics from upstream systems. So we also need to look into how to deduplicate the data at the time of ingestion. And deletes for our application, delete is needs to be considered as like a first class citizen, mostly because with any other with any other user interfacing application, we are prone to accidentally getting sensitive information entered by employees at work. So we always have requests from customers asking to delete specific records in different tables. So we also need to figure out how to handle deletes when we move to S3 Athena-based data lake solution. This was kind of challenging because S3 is just a plain object store that can help create and delete files, but does not support append or like modification of an existing file. So we were looking for some mutability to take care of our delete use case. And then with periodic ingestions and partitioning schemes, we always tend to produce small files. And this would cause performance issues and queries. So we were looking to see how we can take care of small files. And when while we're talking about the small files, we also need to consider compaction and cleaning. They go hand in hand, right? So we needed like a background process that can stitch the small files together for better query performance, and a cleaning process that can get rid of older files to check like unbounded growth in our DFS storage. And then backfilling is yet another use case, right? Like while fulfilling these file sizing constraints that I described above, we also need to ensure that backfill doesn't accidentally produce duplicate versions of records, duplicate records. So that was also one important criteria. And then schema evolution is another big factor to be considered in moving to a data lake solution. Like Postgres did have a rigid schema, but evolution was not a big concern because of the rich APIs that Postgres had. Whereas when we move to a data lake solution, we need to fix the gap of handling these schema evolutions, because all these systems are like schema on read. So we had to be careful about this as well when moving to a data lake solution. So with these, we were trying to see if it would make sense to build these gaps by ourselves, or like to test something like adopt something like Hudi that offers these solutions. So we went ahead and tested Hudi for a couple of our tables, and we really liked the experience going to a data lake with very little effort into fixing these gaps. So with that new architecture, we rolled out all our raw data layer into Hudi, and our new data architecture looks like this, where we have these logs produced by shipped to S3, processed by Hudi pipelines. We use Delta Streamer in Hudi to consume these logs and produce them to S3, and also sync the metadata to AWS Glue. So Athena can then query the Hudi tables Athena also has native integration for Hudi. So it made it easy for us to just switch to Athena and S3 by just using Hudi in our ETL pipelines. With Hudi, we experienced out-of-box support for all these challenges that I described so far. So we didn't really spend time in building these gaps per se. Hudi gave us significant time back in doing our business, rather than spending time in building this infra individually, which would have taken a huge amount of time. But we did have some hiccups and challenges. We learned some lessons on the way in our data lake journey. For example, a few things to mention are like deletes can be easily processed via Hudi, but we discovered that to hand over deletes to Hudi, we had to build internal tools that can discover tables that had sensitive information, and that discovery mechanism should happen, and then hand over the deletes to Hudi. And our Delta Streamer based ingestion was showing up listing performance in certain large tables. We looked into this issue and identified that for for daily ingestions, listing the entire table was not needed. So we contributed a patch. We contributed an implementation of the path selector implementation. It's called the date partition path selector. We leveraged this, and on enabling this implementation, we were able to prune the listing to just last few days of partition instead of listing the entire table. This gave significant gain in like ingestion latencies. Those are few things that we learned, and we are actively, since now we have the metadata based listing, we are actively looking to move towards the metadata based listing instead of the date partition path selector. We hope that will give us even more optimized performance. And while doing so, we will also be leveraging the delete API for our delete use cases. In parallel, we are also exploring clustering of our data sets based on date column. That way, we can contain the fragmentation caused by like frequent ingestions and explicit. We don't have to have like explicit partitioning on dates and have like even more neatly sized files. So I think that brings me to the end of the presentation. I hope I was able to share useful experience with based on our data lead journey. We do have interesting problems, data problems in Moveworks. So in case if you're interested, please check out our hiring page. Thank you. Let me stop sharing and move to the other slide for the roadmaps, and then I can take questions for both towards the end. Okay. Is that possible?
Yes.
Okay. Hello all, it's me again. I'm going to present the interesting roadmap that we have in Apache Hudi open source. We have a roadmap page in the website. This is not an exhaustive list. We just wanted to highlight a few interesting work that's going on. The roadmap, you can, when you hop onto the roadmap page, you can see that the features are categorized into three layers based on our stack. The database layer, the execution engine integration, and platform services. We had a minor release 0.10.1 in Jan, and we have an upcoming release 0.11 in March, and we're very excited because there's tons of new functionalities there, and we really hope like Hudi users can leverage those functionalities, test them, and give useful feedback to improve them further. We also have more releases coming in May and in the summer. Moving on to the 0.11 feature highlights, here are a few. We're working on metadata index in 0.11 as an alternative for Bloom index and Bloom index implementation. So what this is like we often see like Hudi has like a couple of indexing schemes, and we sometimes see that with Bloom index for certain use cases where there are like a large amount of files, the shuffle can there can be large shuffles causing performance issues with the Bloom index. So we wanted to address those type of use cases by leveraging a metadata index that can offer faster performance over the Bloom index, especially for use cases where there are a large amount of upserts for larger tables. Next one is a record level indexing work. Prashant already discussed this, but at a high level, this comes up in the community often where we see people want to try out like random write workloads on workloads and global indexing. So currently there is no solution except to using HBase index or employing external indexes. So with record level indexing in 0.11, we are looking to replace this type of use case by being able to leverage the record level index for handling any sort of an update pattern while making sure that it's fast and performant. And then, sorry, the index column support and elimination of partitioning. There are more details in Hudi 512 on this, but briefly, we are planning to provide an initial support for column indexes. What this does is like provide support on index functions over columns to generate indexed columns. And then we have refactoring and redesign of query side code path. So oftentimes we see in large projects, there are like a couple of rewrites during the lifetime of the project. And we wanted to see like now that Hudi has more than 5 to 6 query engines beyond Hive, we wanted to take some time, look back and see how we can consolidate all our query side code path so that we can provide better APIs and abstractions on them. So this functionality will focus on that. And we are also planning to provide a better support for native encryption for exposing Parquet files and also supporting other type of encryptions. There are more details on about this in Hudi 2370. We also have a couple of connectors in Presto and Trino. With Presto, we have the latest Hudi version merged on, and it's closer to landing that will leverage the metadata-based listing. We also have a Presto Hudi connector from the community that is up for review, which is on par with the existing Hive-based connector. There is also a brand new Trino connector that is up. Please take a look at these, test them, and please provide useful feedback so we can shape them better. And then we also have support for updates and deletes on non-keyed columns while still preserving primary key enforcements. That's coming up in point 11. We are also adding native support for Glue Metastore. Right now, we use Hive-based, like we depend on Hive for syncing to Glue Metastore. Instead, with this feature, we are planning to use Glue APIs directly, which will be more reliable when syncing to Glue Metastores. And we are also, like Hudi has this syncing mechanism to different catalogs, right? So we are planning to extend this support to BigQuery and Snowflake as well. We already have some similar integration with Redshift via AWS Glue. The idea here is to make major warehouses be able to query Hudi tables. There are more details on the RFC if you're interested. Moving on to point 12. Moving on to point 12. We are planning to leverage Spark data source V2 APIs. It comes with cool features for push-down filters and other capabilities. The Hudi read path will move on to V2, while the write path will use V2 while falling back to V1 in order to preserve optimizations on Hudi write path like file sizing, pre-combining, indexing, etc. We have a blog on optimistic concurrency control. Right now, with optimistic concurrency control, we allow multiple writers to process the data while we take in the writes, and finally, before the commit, we check for contention and abort if there is any overlap. But as you can see, this is very resource expensive. And so with this particular feature, we are trying to see explore if we can detect the conflicts early on and abort the overlapping rights if need be. This functionality will also use the marker-based implementation to like detect overlaps among pending transactions. There are more details on Hudi 1575 if you're interested in exploring this. And then we have index timeline and infinite retention of versions. Right now, the Hudi timeline goes through aggressive cleaning and archival, so we can bound the amount of data in the timeline. This is done for like bounding lookup issues and also for making sure that we don't like unboundedly grow the timeline data. In point 12, we are looking to index the timeline as well to serve this metadata in a scalable way. So we don't have to worry about aggressively cleaning and archiving. Instead, we can have infinite versions of the table while still supporting faster write latencies. And then we have full CDC data model support coming in 0.12. With this, we will hand out Debezium-like semantics in our incremental queries. Today, we have incremental queries handing out just a change that happened out of updates, inserts, or soft deletes. With this feature, we're looking to give like a pre and post image of the change along with commit LSNs and what operation caused this change. Like, for example, whether was it an update or an insert or a delete, etc. And we are also building a hash-based file index, which will complement the bucket index to scale elastically and solve for cases where the Bloom index would be like would produce like false, high false positive rate. So we're looking to build a hash-based index for solving such type of use cases in Pointwell. And we are also looking to add ORC support, much like Parquet. Right now, it's just available in Hive, but we are looking to expand this to other query engines as well. And add CDC stream support for Kafka Connect Sync. So today we have only append-only use cases on the Kafka Connect Sync, but in Pointwell, we are expecting to see CDC stream support as well. And you'll also see more integrations in Pointwell. For example, the Apache Pulsar as a data streamer source, and then Hudi Airbyte Sync and Kinesis DynamoDB's CDC support, etc. So that's for 0.12 highlights. Like I said, again, this is not an exhaustive list, so please go over to the roadmap page and see if you need more details. We do have a few big rocks for coming up for 1.0, and we really look forward for the community to contribute to this and provide useful feedback so we can improve. Some of the highlights there are Meta Server. The idea here is like we currently have a medley of services for different purposes, like for example, HMS and Zookeeper for locking. We store the table metadata in different catalogs, and the file level statistics are sitting in DFS, the cloud storage. So for an average user, this could be like a huge number of services. So we wanted to make it more simple. And so we're trying to design a meta server that could be Kubernetes compatible and can serve all the timeline, table metadata, and locking support much more efficiently. So this work would focus on these areas. And we also have a caching layer coming up that would like enable even more real-time lakes by making use of the log compaction functionality for MOR queries. The caching layer would be transaction aware and would build upon the multimodal indexes and the meta server that we talked about. We already have a couple of concurrency control techniques that we are using today. The lock-free concurrency control will aim at exploring how to achieve lock-free concurrency control. The idea here is to use you can see the Hudi 3187 for details, but the high level idea is to see if we can leverage the transition time for every action in the Hudi timeline as well to see if there are any contentions. We can also expect more cloud native ingestion support in Delta Streamer for other cloud object stores. We have this implemented for S3 already. This area would focus on GCP, Azure, and other cloud stores. So I think, yeah, that comes to the end. So there's been like an interesting set of things that are coming up in the roadmap, and we really want the community to participate and see like how useful they are. You can engage in different ways here, like please hop onto the Slack if you just want to say hi to other fellow users or ask questions. We have a very lively community in Hudi. So thanks for taking time. I can open up for questions now.
Thanks, Sudha, for sharing your Moveworks journey and also sharing what the Hudi community has been up to. Seems like a lot of exciting new work is happening, and I see a lot of companies contributing. So Awesome to see that. I think we are out of time. If you want to take a couple of minutes to quickly answer the questions, we can do that.
Okay, I have a question on what's the difference between Spark DS V1 and V2. I guess like with V2, we have much more features that we can leverage for our read path. I can get back in Slack on this for further details. I can point you to the resources. I have one other question from Rajesh. Did switching Postgres out for querying still meet your read SLAs? Yes. While read SLAs are like critical, like it also depends on what type of use cases you have for the data analytics, right? We were still able to get like acceptable query results from our data lake, even when we moved out of Postgres. So that was not an issue. There are more questions here, but I can take them offline.
No, let's take some time. It's okay. Yeah, let's take the time to answer the more questions.
Okay. So are there EMRs running 24/7, and how about the cost? No, we are not running EMRs, EMR cluster 24/7. We run them based on need. Like we just spin up clusters whenever there is a Airflow job that's being triggered. When we migrate from Spark 2 to Spark 3, historical dates are not supported from RDD API, but supported in data frame API in Spark 3. Is there any plan for Hudi to upgrade to data frame API from RDD? So this work, this will be touched based on, like this will be answered by the Spark data source V2 again. I can point you to the details offline on this. I think there was one question on why Presto and Redshift Spectrum, why not one or the other? I don't think this was meant for me. Maybe Felix?
Yes, I already answered that one. So that is the reason I didn't just type in, because I just mentioned why we were using the Redshift Spectrum, because some data we were having in the Redshift. And in that case, we will use the Redshift Spectrum. But yeah, so that we already answered.
Yeah, I think those are the questions.
Okay, sounds great. Yeah, folk, if you have more questions for from a Hudi perspective, please reach out on the community channel and the community Slack channel, I think, that the open source community has, and other community members may also be able to help answer these questions. So thank you so much, folks, for joining. Thank you to all the speakers for taking the time to prepare the slides and share with us all your learnings. And we'll see you in the next session.
Thank you.
Bye.
Bye.
Thank you all.